This is the video for the Unit 5 Section 1 Notes Part 3 on the combined gas law. So the combined gas law is a combination of Boyles's, Charles's, and Gay-Lussac's gas laws. We use this gas law if a gas undergoes a change of pressure, volume, and temperature all at once. And really, this law is used if the same amount of gas is present, so at constant number of particles. You can see the gas law down here. You may see it being familiar to Boyle's law in that pressure is multiplied by volume, similar to Charles' law in that volume is divided by temperature, and similar to Gay-Lussac's gas law in that pressure is also being divided by temperature. We can see our initial conditions on the left side of the equation and our final conditions on the right side of the equation. So let's actually take a look at how we'd use this mathematically. Let's say we have a situation where we know that a gas-filled balloon has a volume of 30.0 liters at 313 Kelvin and 153 kilopascals of pressure. And we want to know what the new volume would be if the gas was brought to STP, or standard temperature and pressure. So let's go ahead and list our conditions: our initial pressure, our initial volume, our initial temperature, our final pressure, our final volume, and our final temperature. So we know the initial pressure is right here, 153 kilopascals. We'll record that down below. We know our initial volume is 30.0 liters, and we know our initial temperature is 313 Kelvin. Now, it doesn't say it directly, but we know we're looking for final volume, and we also know pressure and temperature are these standard values. That's what STP stands for. We should know that pressure at STP is always 1 atmosphere, and temperature is always 273 Kelvin. We'd see down below, volume, our final volume is what we're looking for, and all of the other variables have been defined. Notice that pressure, our initial pressure, is in kilopascals. Now we want to convert this to atmospheres before we get started. We'll set up kilopascals over 1, multiply by our conversion factor. 1 atmosphere always equals 101.325 kilopascals. Cancel out kilopascals, multiply straight across numerators and straight across denominators, and then divide to get 1.151 atmospheres. Let's go ahead and rewrite that on the left side. And now we can actually solve out the combined gas law. We'll first write our equation as always, and then plug in the values that we know. Notice that volume 2, what we're looking for, we left as volume 2. I'll then multiply by a reciprocal fraction so that 273 Kelvin cancels top and bottom, and 1 atmosphere cancels top and bottom, so that we're left with just that final volume. Now in red, that's our algebra step. What we do on the right in algebra, we have to do on the left side of the equation. So we'll copy that down over here. Now the numbers don't cancel, but the units of Kelvin will, and the units of atmospheres will as well, because we have 1 in the numerator and 1 in the denominator. Finally, let's rewrite all of our work on the left side. Everything that didn't cancel gets rewritten. We can see that 273 times 1.51 times 30 liters divided by 313 Kelvin equals V2, or the final volume. Notice the only unit left over is liters, which is good because that's the unit of volume. We'll multiply our numerator, divide it by our denominator, and get 39.5 liters as our final volume. Now in the past, with our initial gas laws, we could kind of logically say what was going to happen to the unknown variable. In this case, it's a little bit tougher because there's too many things changing. When both pressure and temperature change, it's hard to get a sense of what will happen to volume, but we can calculate the actual effect. We can see volume increases from 30 liters to 39.5 liters. Now let's take a look at a second scenario with one slight twist. In this scenario, a gas at 1.53 atmospheres, 298 Kelvin, has an initial volume of 1.00 liters. We're going to say the pressure will increase to 5.97 atmospheres, and the volume decreases to 0.3242 liters. And we're asking what that final temperature of the gas is in Kelvin. Let's first list what we know. We know the initial pressure is 1.53 atmospheres. The initial volume is 1.00 liters, and the initial temperature is 298 Kelvin. Final pressure is 5.97 atmospheres, final volume 0.342 liters, and final temperature is our unknown. That's what we're looking for. We'll set up our equation, plug in everything that we know. Notice that T2 stays the same, and just like in a previous example, notice that T2 is in our denominator. Now we need to get that out of the denominator one way or another. My preferred method is that because everything in our equation is a fraction, we can simply flip everything. Notice both of my fractions, I flipped them. I'll then multiply by my reciprocal fraction so that 5.97 atmospheres cancels and 0.342 liters cancels. That'll get us just T2, or final temperature, on the right. We'll do on the left exactly what we did on the right side, canceling out our units of atmospheres and our units of liters. We'll then rewrite our math on the left side. 5.97 times 0.342 times 298 Kelvin divided by 1.53. These ones don't really matter. They don't affect anything. And the only unit remaining is that Kelvin, which is good because we're looking for a temperature. Once we multiply out our numerator, divide by our denominator, we should find our final temperature is 398 Kelvin. I hope this helps you understand how to use the combined gas law to calculate a final condition if pressure, volume, and temperature all change.